Alright, so we are back for day 3 of physics, and we'll be talking about atmosphere pressures and PaO2. Also, we'll be talking a little bit about hypobaric and hyperbaric oxygen. Alright, so atmospheric gases. So when we look at atmospheric gases, we're looking at the molecules in the atmosphere, how they're colliding with each other in a container, and that actually will create a pressure. Okay, so this is also referred to as the barometric pressure. So barometric pressure is the force of what the atmosphere is applying on our Earth, depending on where we are. Okay, so there's obviously a lot of air above us, and so we describe that or define that as atmospheric pressure, the force that it's applying. So there's actually, it's kind of impressive, there's 14.7 pounds per square inch. That's how you read that, of atmospheric pressure. So if you look at your hand, your palm, which is about 20 inches squared, that would actually equal then to about 294 pounds pushing down on your palm. Okay, so this is just the source that came from. It's not I mean, it's a link you can look at if you'd like, but it's not a video link. The scienceabc.com. So pressure, why we don't crush under this force, why we don't crush our bones or our body under this atmospheric pressure, is that there's also pressure that is exerted back into or onto the air molecules by the inside of our body. So it achieves a state of equilibrium. Okay, but keep in mind that gravity affects your pressure. Okay, so depending on your elevation affects your atmospheric pressure. And so when we think about that, so what happens with gravity, how that works is that gravity is going to then increase your gas density. And then increasing that density actually increases the rate of molecular collisions and then gas tension. So that's why when we are at increased gravity, we'll see an increased density, and then increased altitude, so we have less gravity at elevation. So you think about being up in the space station or whatever where you don't have any gravity, there's also decreased density, so things tend to float. Okay, so when we have increased altitude, we have decreased density. When we have increased gravity, then we're going to have increased density. So in Colorado, we actually are far enough away from sea level to see a pretty significant difference in the barometric pressure. So the barometric pressure is something, obviously weather forecasters and that use to help determine weather patterns. But it was kind of interesting. This is just way old school. Back when I was working in Wisconsin, we did, and they do it here too, metabolic studies, and it depends on, and you'll see here coming up in a few slides, how much atmospheric pressure there is can also be dependent on gas diffusion. Okay, so how much oxygen is available. And so we used to have to call a phone number, I remember, every morning to get the barometric pressure so we could put it into our calculations to figure out like A to A gradients, big A meaning alveolar, little a meaning arterial. So you'll see how this kind of plays out here in a couple slides. So just know that sea level is generally considered 760. Okay, that's sea level, 760. In Denver is actually about 640, so it's considerably less. So atmospheric pressure then is measured with a barometer. I do have a little video link here that kind of gives you a little bit of a history and how the barometer works. It's about a 5-minute long video. So it is measured, pressure then is measured is a force per unit of area. So pressure is a measure of force per unit area. And the SI, that standard international unit of pressure, is measured in a Pascal, that's the PA, Pascal, or the N means Newton. Newton, like a Fig Newton, N-E-W-T-O-N, or Isaac Newton. You can tell I'm hungry. Newton per meter squared. Okay, so that's the N/M2. Okay, so what you have, and you'll see it in the video and you'll see it in the picture coming up here, is that they take a long tube that's filled with mercury and then they invert it into a pool of mercury. So they kind of put it upside down, and then the atmospheric pressure actually pushes on the pool and then actually makes the tube then fill up. Okay, and then however many centimeters or millimeters, depending which way you're looking at it, well, we'll talk about that in a minute too, but it's generally millimeters, centimeters or millimeters is measured, like, you know, inches or whatever along that tube, and then how much it's pushed up is how much the barometric pressure is. Okay, so so this little video kind of shows you that. So at sea level, then the barometric pressure will actually push on that pool of mercury and cause in the column in the middle to actually rise about 76 centimeters, which is equal then to 760 millimeters of mercury. So I highly recommend you watch that video link. Alright, so this is kind of what I'm talking about as far as the tube being inverted. So you have this tube, and I believe this is out of Egan's too. If you look at Egan's, about page 116, yeah, 116, around that area, give or take a page, it talks about barometric pressure in that textbook. And then you also see another one on the right side there. So you have a vacuum that's created, and so that one is 760 millimeters. So depending on your increments of measurement. And then the last one there, the little dial on the right, that's an aneroid, A-N-E-R-O-I-D, aneroid barometer. Those ones aren't quite as accurate, but they can also kind of give you an idea of the barometric pressure. So, so this basically means that in the upper right one, this means that the atmospheric pressure is great enough to support a column of 760 millimeters of mercury. Okay, so mmHg. Okay, that means millimeters of mercury. So your Hg then, when you see it written mmHg, millimeters of mercury, Hg is your symbol then for mercury on the periodic table of elements. So again, the height of the mercury column represents the downward force then of the atmospheric pressure, and it is then either measured in inches on the one on the left, or milliliters or centimeters. But then barometric pressure then is reported in either inches or millimeters of mercury. And we'll talk about the conversions here. You'll see it in just a couple slides. Alright, so this is another way. You'll find this actually more so in a plane. So barometers can also be used as altimeters, or altimeters, I think. So you can kind of see the different readings there and what it all means. You're looking at altitude, and then you're looking at barometric pressure. So that's just a altimeter. So if it's a pressure altimeter, it can also be, or altimeter, it can be used as a barometer. Alright, so here are some of our different equivalents. So we have 760 millimeters of mercury again. This is at sea level. Okay, it can also be referred to as a torr. Okay, and that is for the gentleman that, did I skip the name on the page when we were talking a minute ago? I might have. Oh yeah. So the long tube that's filled with mercury, then it was inverted into a pool, was by Evangelista. That was on one of your other pages. Torricelli. Okay, so that's where the Torr comes from as part of his last name. It was also done in water by Gasparo Berti. So 760 millimeters of mercury equals 760 torrs. So 1 torr equals 1 millimeter of mercury. You might also see it as 1 atmosphere, ATM capitalized, which is also then equal to 14.7 pounds per square inch, which is also equal to 39.9 feet of water. All right, so conversion factors here then. So if we're looking at 1 centimeter water pressure, this then is equal to 0.7355 millimeters of mercury. So the two last ones are probably the ones that I really want you to know as far as being on a test. I mean, if you can memorize the rest of them, but the ones that you're going to probably see more often. So you just want to definitely know that 1 torr equals 1 millimeter of mercury. And then 1 millimeter of mercury actually equals 1.36 centimeters of water pressure. Okay, so you can convert those. And that is probably the one I have highlighted in my notes. For some reason I couldn't remember somehow at some point changing it. So just know that that would probably be a board question on your boards. So 1 millimeter of mercury equaling 1.36 centimeter water pressure. All right, so all this pressure talk. So partial pressure. So we want to define partial pressures, which is Dalton's law. Okay, so that is the pressure that is exerted by a single gas in a mixture, which is then referred to as its partial pressure. So Dalton's law is going to describe the relationship between the partial pressure and the total pressure in a gas mixture. And this YouTube video link can help explain it to you also. So we actually do watch this when I'm teaching it in class, but so I definitely highly recommend that you watch that. So Dalton's law then, so this is how we kind of apply it, and this is out of page 116 in Egan's. So if you're looking at an example of gas making up 25% of the mixture, which would exert then 25% of the total pressure. So the percentage of the gas mixture is generally expressed in decimal form. That fraction concentration, it can also be referred to as mole fraction. And we kind of talked about this before when we're looking at, like, for example, if we have a 25% of a mixture of gas that has a fractional concentration, then is going to have a fractional concentration of 0.25. So a gas that has a 25% of a mixture has a fractional concentration of 0.25. So just knowing how to convert from percentage to decimal, because when you do your math here, as you can see coming up, we're going to be working with the decimal part. So when we're looking at the fractional concentration of oxygen, and we should know that by now is 0.21 or 0.21, okay, or 21%. Okay, how much pressure in the atmosphere then is created by the oxygen? Well, it depends on how much barometric pressure there is. So at what elevation are you at? Okay, so the amount of oxygen is going to stay the same. It's always 21%. Okay, so you have the 0.21, and then you're going to multiply it by 760 if you're at sea level. Okay, so then that equals to 160 torr, or 160 millimeters of mercury. Okay, so that's how much pressure of oxygen is in the atmosphere. Then if we're looking and we're comparing these two, we're looking at nitrogen, And nitrogen, the percent of nitrogen in the air, in the room air, regular air that we're breathing, is 79%, or 0.79 for the math part. And then again, if you're at sea level, you're multiplying it by 760, and that's going to give you 600 torr. So then you can see, if you add those two amounts together, 160 and 600, you get 760, okay, because that's what the air is made up of, okay. So how is this different when we're at elevation? Okay, so why is it at elevation we need more oxygen? And even here at this elevation, we need more oxygen. Most of us can compensate for it. Our bodies adjust. We produce more red blood cells after a period of time, especially if you're living at elevations of like 8,000, 10,000 feet. You definitely become polycythemic. You get a thicker blood to help carry oxygen. And that's why some patients living here in Denver may need oxygen, but if they go down to sea level, they may not need their oxygen, you know, depending if it's cardiac or pulmonary related. So because there is more partial pressure available for them. So we'll look at this example coming up right here on the slide. So again, the fractional inspiration of oxygen is the same. Okay, it's still 21%, no matter where you're at, as long as you're on this planet. Okay, so you have an FiO2 is always 21%. But when you're at elevation, so you go climb Mount Everest or whatever, and you're at 25,000 feet, the barometric pressure there goes down to 282 torr, or 282 millimeters of mercury. So then the available partial pressure of oxygen is quite a bit lower. So you do the math, you have the 0.21 still, you still have the 21%, but you're multiplying it by a much lower number. So then you only get 59 torr, or 59 millimeters of mercury. So that's about 2/3 lower that's available at that elevation than would be at sea level. So when we look at flying, for example, so those the planes are pressurized, so they're pressurized to be equivalent to, hopefully, close to sea level, or wherever the plane came from. So let's say we're at 30,000 feet. The partial pressure available then is even lower yet. So we have 21.21, or the 21%, times 226. That's the barometric pressure at 30,000 feet. So then, all right. So before I was rudely interrupted by my dog once again. Sorry about that. So again, as we climb up in elevation, so when we're at 30,000 feet, then that pressure that's available is only 47 torr, or 47 millimeters of mercury. So the oxygen that would drop out of the plane if you were to lose elevation fast and it wasn't able to pressurize delivers about a 70% oxygen, so it's really not quite 100%. Okay. So what do we need to do with all this wonderful information? So this is going to help us calculate our alveolar air equation. This is something that you're going to want to memorize. Okay, so you'll actually have excuse me, practice coming up on your homework. It's only like 5 problems, I believe, but you're going to be given a variety of barometric pressures. Okay, and we always have to subtract the pressure of water vapor. Okay, so the water vapor, which is normally 47, varies a little bit with temperature, but as a standard, okay, so standard, you're going to always take your barometric pressure, you're going to subtract 47, you're going to subtract that partial pressure of the water vapor in the alveoli, and that's generally 47 is at body temperature. So you'll take 760, which is our normal, minus 47, Okay, then you're going to take that difference between those two numbers, multiply it by your FiO2, or your fraction of inspired oxygen. So in this case, you're multiplying it by 0.21. Okay, so it would be 0.21. So you're going to plug in all your values here. So your FiO2 is 0.21. You have 760 minus your 47, so that's the difference between those two numbers is the number in your parentheses. So remember your PEMDA, you're going to do the parentheses part first. Okay, you have no exponents. Then you're going to multiply 0.21 times, what is that number? I think it's 713 if I remember right. And then whatever value you get there, put that like up above it or whatever. Then you're going to take your PaCO2, remember from before, that's the partial pressure of carbon dioxide, which is in your artery. Okay, so little a is artery, big A is alveoli, and that's generally between 35 and 45. So for these problems, you're going to be given a PaCO2 value. Okay, so they'll give you one. It's not going to be a range. They're just going to give you a number. So you're going to take that number, multiply it by 1.25, and then whatever you get for those, the multiplication of that, you're going to take that away from whatever your FiO2 times your barometric pressure minus your water vapor pressure. Okay, so it'd be like, let me do this one for, let me hold on one second. Alright, so if we do the whole math with this, so if we're using this equation, our FiO2 again is the 21%. If we take 760 minus 47, we have 713. So if we take 713, you multiply it by 0.21, you should get 148. Okay, so that is this top part here. Okay. So if you take it by 0.21, you should get 148. Okay, that's taking the 760 minus 47, which equals 713 times 0.21. All right, then you're gonna take, let's use a PaCO2 of 40. Okay, if we use a PaCO2 of 40, we'll use a number right in the middle between 35 and 45. Okay, for easy math's sake. So if we take 40 times 1.25, that's going to give us 50. So now we have 148 minus 50. That is going to give us a PaO2 of 98. Okay, and that is considered normal. Okay, that's the partial pressure of the alveoli. 98. Okay. All right. So that's how you calculate your alveolar air equation to get your PaO2. All right. So moving on to a couple other different conditions that you might experience. More so hyperbaric. We actually do have a hyperbaric. I think they have one at, I want to say St. Joe's University. So a hyperbaric is a place where you're going to have pressure above than that atmospheric sea level pressure. Okay, so greater than 760. So that would be found then below sea level. Okay, so if you are 66 feet, for example, under the water, you're going to experience a pressure that's 3 atmospheres, or 220 or 2280 millimeters of mercury. Okay, so the pressure then available, so you have such a big number to work with, the pressure available for the oxygen delivery is going to be 3 times that amount at sea level. So ocean diving, of course, but you have to be careful because you can kind of feel that pressure, I guess, on your body. I don't know, I've never done deep sea diving, but I imagine that's how it would feel. And then a hyperbaric chamber. Okay, so we'll talk about indications for a hyperbaric chamber here coming up. And then hypobaric then would be exactly the opposite. pressure below sea level or pressure below atmospheric pressure, which below 760. So that would be found above sea level. So remember, it was kind of like a kind of inversely proportional there. So hypo meaning below atmospheric pressure, but that's going to be found above sea level. So you're talking elevation in an airplane. This is just a little picture of a RT working in a hyperbaric chamber, and some of the things that we would treat, different conditions that we would treat in a hyperbaric chamber are definitely infection. So you think about, you have 3 times the higher than normal atmospheric pressure, and I think they can go like from 3 atmospheres to like 5 atmospheres, so they're definitely a range in them. And then there's definitely a protocol always obviously involved. I think they have to kind of bring it down really slowly. I'm not really sure the specifics on it, but so some of the different things to hyperoxygenate would be gangrene, a burn patient, to help treat decompression sickness or the bends, and carbon monoxide poisoning, because carbon monoxide has greater affinity than oxygen to the hemoglobin. Okay, so that was a little bit shorter. Hopefully it wasn't too terribly bad. Again, your homework is going to be calculating your PaO2, and just be mindful of looking at all your different numbers. When you have to take all of those problems and make sure you minus the 47 millimeters of mercury. So your P for your H2O, your pressure of your H2O is always going to be 47. So you always have to subtract that no matter what barometric pressure you're given. Okay? All right, email me with questions. Have a great holiday weekend.